All right, we have now know several ways to make monosubstituted benzene rings. Now, please note, looking at this chart, there are two compounds that we did not cover, those two right there. If they look unfamiliar to you, that is why, because we have not covered those reactions, so you are not responsible for knowing those. But the rest of these reactions we actually have covered, and you should know those by now. But what about benzene rings with more than one group on it? Okay, to synthesize these, we need to discern the order that the groups must be put onto the benzene ring. This will be determined by something called the directing effects of each group. Okay, we will be discussing these effects for the remainder of chapter 18. Substituted benzenes, meaning a benzene ring that already has something on it, may undergo electrophilic aromatic substitution reactions with faster rates than unsubstituted benzenes. Okay, toluene, for example, undergoes nitration 25 times faster than benzene alone. The methyl group, what we call, activates the ring through induction, makes it a better nucleophile. Substituted benzenes generally undergo electrophilic aromatic substitution reactions regioselectively, meaning we will not see the group that's coming in adding to all of the positions around the ring. They will prefer to add to either the ortho and para positions, or they will prefer to add to the meta position relative to that group that's already on the ring. Okay, whether the incoming group prefers to add to the ortho or para positions or the meta position will depend on what substituent is already on the ring. Okay, so again, let's go back. For toluene, which has a methyl group attached, we can see that when we add a nitro group, it prefers to go to either the ortho or the para positions. Okay, we get more of those two products. Okay, very little of this nitro group adds to the meta position relative to the methyl group. Okay, again, remember, when we do these electrophilic aromatic substitution reactions, we're only adding in one group at a time. Okay, toluene will send it to either, even though there's two choices, it will go to either the ortho or the para position relative to the methyl group. So why is this? It has to do with the stability of the carbocations that are formed in the sigma complex intermediate. If the nitro group adds to the ortho position, the first resonant contributor of that sigma complex is a tertiary carbocation. We know that tertiary carbocations are more stable than secondary carbocations. When the incoming nitro group adds to the para position, we can also get a tertiary carbocation formed as one of the resonance structures in the sigma complex. However, when this incoming nitro group attaches to the meta position, this position right here, we do not get a tertiary carbocation formed in the sigma complex. Since we know that tertiary carbocations are more stable than secondary carbocations, the products that have a tertiary carbocation in the sigma complex intermediate are more stable and thus more likely to be formed. The methoxy group in anisole activates the ring 400 times more than benzene, meaning reactions of anisole are 400 times as quick as benzene. The methoxy group donates electrons to the ring through resonance. Since it is donating electrons to the ring, it makes the ring a better nucleophile. Any group that donates electron density to the benzene ring, making it a better nucleophile, is what we refer to as an activator. Activators, or activating groups, such as methoxy over here, are generally ortho-para directors. Again, we can see that the sigma complex is more stable when a group adds ortho or para to the methoxy group. This is because we have extra resonance structure stabilizing the sigma complex, which makes addition to either of these positions more favorable.